Swayam Prabha. Digital India. Educated India.
We're going to start with the most basic side sway case. There's nothing more basic than a cantilever, right? So if we take a cantilever column, again we got an EI star because in the Americas we like to play around with EI and put reductions on it. Length L, we've got a lateral load, so you could say this represents a story of a building, a lateral or a story shear, H. Now, obviously, we have a moment at the base. That's our lateral moment in the system, HL. And clearly, the stiffness would be 3I/L cubed, correct? So if we want the deflection, we call that delta H. That's the first order deflection due to the story shear, H, delta H, okay? And then Lemessurier was essentially the person that really coined all the arrangement of the equations that I'm going to show to you here. The word on the street is that the subscript L there is for Lemessurier, but maybe you could say it's for lateral. It's a PL story, and you say, well, P? Okay, yeah, we'll see why we call it a P, but think of it as a story stiffness. But it's a little bit different definition of story stiffness than what we used in the denominator there and what we just walked through. PL story is the lateral load H per unit drift ratio or unit rotation, delta H over L, if you wish. Okay, and of course that would be then for our cantilever 3I/L squared. And so the drift ratio we can obviously get by dividing H by the stiffness, written in this way, PL story, or H is PL story times the drift ratio. So now let's get a little more fancy. Now we've got a cantilever with some other parts of a structure that are tied to it at the top of the cantilever. It's just a pendant strut that's tying it to a column over on the right. Column over on the right is what we would call a leaning column because it's pinned top and bottom. And so if I took away the strut, what would happen to the column on the right? It has no stability. It would just fall over, right? So that means it's leaning on the lateral load resisting system, represented by our cantilever on the left. And for purposes of our initial discussion here, let's say that the gravity, the only significant gravity load or vertical load on the system is P1. That's on our leaning column. We have a story shear or a lateral load on the story H, and the question is, okay, so what is the second order deflection, the story drift, delta second, given these two loadings on our story? So let's subdivide our frame here into two free body diagrams, one of the leaning column. And so we can see in the leaning column, since both ends are pinned, if I get a side sway, I'm going to have a shear equal to P1 times delta second over L, right? That's required for equilibrium in the deflected geometry, right? We're talking about equilibrium in the deflected geometry, second order analysis. And then the free body diagram on the right, Newton's third law, the force is transferred to the horizontal strut there at the top and then over to the cantilever. And guess what? Our story shear at the bottom of the cantilever is H plus P1 times delta second over L. And also we can see that, our lateral moment got increased. It's now HL plus P1 times delta second. Okay, very nice, but we haven't figured out what delta second is yet. And that's the nature of geometric nonlinear analysis, is the delta second depends on the loading, but the second order effects depend on delta second. And so generally we have a nonlinear problem. A few definitions here. I thought of taking these out, but then I left them. In India, do you design allowable stress design in some situations, or is it all factored loading? No, it's all factored loading. Good for you. We just finished a 2.5 year long debate or configuration with ASC 7. There were a number of prominent engineers, practicing engineers, and some academics on the AIEC specification committee, and it was observed that the load factors in ASC 7 for allowable stress design were such that with certain wind load or earthquake load dominant cases, you could literally size a member or a structure with about 2/3 the size of what LRFD would require. And so there was a long discussion. Does that mean it's unsafe? It's not very good. And to make a long story short, the steel committee, at the chagrin of the steel industry in the U.S., basically said, "Look, we're going to do our own loadings if that's going to be messed up." I said, "No, that's not going to work. That's not going to work well." The number of engineers were also on the ASC 7 committees, so it's been a long period. ASC 7 decided they would look to address the issue. It failed ballot in the last ballot on for I guess that would be for 2027 ASC 7. But now in the ballot that was for the last one. For 2027, it's just passed in November. They were able to get the problem sorted out. One of the solutions, and the solution that failed, it was kind of a clever solution. So we have LRFD load combinations that have a more scientific or probabilistic basis. Some of the ASD combinations were kind of more historical, so that's where things got all messed up. And the clever solution was that, well, just take the LRFD load combinations, divide by 1.5, adopt those as the ASD load combinations. Well, in ASC 7, we have a 1.4 times dead load. Divide that by 1.5, you've got a load factor less than 1. So some engineers look at that and worry. Oh, and you got a resistance factor on the other side. It's okay. And then 1.2 dead plus 1.6 live, divide that. Okay, so the engineers that prefer ASD want to see dead plus live. That's our load combination, is dead plus live. I'm designing some rigging for something. I want to be able to do dead plus live. All right, so we have dead plus live now. They've sorted out what, by reliability basis, what the other ASDE factors should be. Problem solved, but it's been a 2.5 year mess. And if we just had LRFD and not ASD, we wouldn't have been losing all that time. But anyway, I'm digressing. So in the AISC specification, AIC likes to give no preference to one or the other officially. And so we handle things where if it's LRFD, they have a factor alpha, so we can't use an alpha critical in the American spec because we use alpha for something else. And that's equal to 1 in LRFD. It means, okay, we're at strength load level when we design by LRFD. ASD, okay, we need to multiply by 1.6 to get to a strength load level to do our analysis to consider second order effects. Then we divide by 1.6 to get back to a working load level. You should be thankful that if you don't have to deal with that. Okay, so I've got an alpha in here, but that's the last time I'm going to say much about ASD at all, since you're not using it. And you can, everywhere you see an alpha here, you can say, let's take that equal to 1, and we're doing load and resistance factor design or limit state design. So what did I just bring up here with these equations? I got a delta second, and the here in this example, P1 is alpha P story. P1 is the entire story vertical load. And you can see, okay, that's just my shear on the lateral load resisting system, H plus alpha P story times delta second over L, right? If I want my deflection of the cantilever, I need to divide that by 3I over L cubed. Then the second equation puts that in terms of the stiffness PL story. Okay? And so, all right, so we can solve that for delta second. But now we have delta second on both sides of the equation. So we need to simplify the equation and solve for delta second, right? So that's where we'll do a bunch of algebra. So if we carry through all the algebra just to solve that let's solve for delta second over L. What do you know? We end up with delta H over L, where delta H is the first order deflection due to H, times an amplifier, 1 minus P story over PL story. Now, P story is basically the total vertical load that the story is supporting. PL story is the total story stiffness. Now, let's look at a layman's definition of story side sway buckling. What does it mean if we have buckling to a layperson? Well, I've got a structure here. I change the load a little bit, or I disturb it a little bit, I get a huge change, right? Or another way we can say it, well, I've got buckling if the amplifier is becoming huge. So our side sway amplifier here, when will that essentially blow up on us? Well, if alpha P story, we assume hopefully we're designing something where alpha P story is not equal to PL story, otherwise it blows up. But if we scale that by gamma critical, okay, that's our eigenvalue, the amount that we're scaling our loads to get to incipient elastic buckling. If gamma critical times alpha P story is equal to P story, the amplifier would blow up if we put a gamma critical there in the numerator, in that term inside the denominator of the equation. Okay, and so we could say, well, generally, how can we calculate a story buckling load? Calling it gamma critical story here. Again, there's places where I may refer to it as a gamma E. I'm hoping in the AISC standards we can move to something where subscript CR means elastic buckling in all cases, but we're not quite there yet. I think the cold form steel, the AISA cold form steel standard is very close to that. P story, in this example, P story is P1 because P1 is the only load on the story. That's correct. So, go ahead, question, pardon? P story is the load.
Story, as you said, is the story stiffness, is it?
Correct.
So then it's
story
not,
stiffness in terms of drift ratio.
then it's not dimensionally consistent, right?
No, PL story,
on the first slide, it's P divided by delta H by H something.
Yeah, no, it's dimensionally consistent. If you look at PL story, that's units of kips, or kips per radian, if you wish, because it's a stiffness, or I'm going to go to kips. I'm in imperial units again, kilonewtons, okay? PL story is kilonewtons per drift ratio, which you could say is in radians. So that's kilonewtons, right?
Okay.
So yeah, but good question.
Right. Okay. Thank you.
Okay. Now we can take in the lower right here. You can see we can take the drift ratio and say, well, the second order drift ratio, delta second over L, is the first order drift ratio And then we could write, given gamma critical story, we could say, well, our amplifier is 1 over 1 minus 1 over gamma critical story. Okay? So this is really basic story sidesway and amplification. I'm very fond of the way we set it up in this way in the AISC standard. And the emphasis that I'm trying to make here, what we're doing is everything is going to play off of story stiffness, or PL story. So given whatever your structural analysis model is, you can say, okay, I can use my model to get a story stiffness. Do I have some shear deformations that are important in my story? Okay, get your story stiffness, including shear deformations. Whatever it is. Oh, you've got a partial truss system, anything. It's a story sidesway stiffness. Okay? All right, so now let's move to doing the moments. And so we just derived these equations that are still showing up, or I've brought forward to this slide. And now let's say, well, I want to know my sidesway moment. So that's the moment at the base of the cantilever here. HL plus alpha p story times delta second. Delta second we can write as the first order delta H times the amplifier. And at this point, we're going to do a lot of algebra again. Okay, so just algebraic manipulation. And what do you know? M second works the same way for the frame that we have here. Okay? We end up with OHL, that's the first order sidesway moment. And well, what's the second order sidesway moment? You hit it with the same amplifier, same sidesway amplifier. All right, that's the simple case. Now let's suppose we've got some gravity load also on the lateral load resisting system. So the leaning column on the right here, that's just a surrogate for, I could have a whole bunch of gravity framing that's just columns that aren't providing any stability or any resistance to load themselves, but are carrying vertical load to the foundation. So I've got my one column here on the right that's representing that, and then the cantilever is representing whatever is providing my story sidesway stiffness. Question?
So in the previous slide, when you said second order moment, you're talking about the small delta effect?
No, it's not a small delta.
Then the second order, we already included in the calculation, right?
Okay, so if let's look at what we got here. So we're focusing on P small delta all yesterday. There is no P small delta in this frame.
Okay, but when you say M second order, HL plus P delta is what we already considered in the calculation.
You're right. Fundamentally, if I want to know the second order moment, if I got delta second, it's HL plus P1 times delta second.
Right.
Done. But we like to write. We like to typically write what's delta second? Okay. All right. So that delta first times an amplifier.
So you're just plugging it in. Okay.
Right. And then we typically want it, is typical practice to say, oh, I've got a first order moment. What's the second order moment? Well, first order times an amplifier.
I see. Okay.
But you're absolutely right. That's the HL plus P1 times delta second. That's the fundamental thing that's happening. It's equilibrium in the deflected geometry. Right.
Yeah. Thank you.
Good. I'm glad you pointed that out, because that's something I like to try to emphasize, and usually something that flies over everybody's head. All right, so here, let's see if I'm to the place I want to be. Oops, I'm going backwards, no wonder. Okay. All right, so we're just here. And then we were, what am I, okay. All right, so I've just moved to this slide, and no, we already did this one, okay. All right. Okay, so there's our amplifier on the sidesway moment. All right, so now we are complicating things by saying we also have gravity load on the lateral load resisting system. We're calling that P2 here. So clearly, in this problem, we've got the same effect coming from the leaning column, but now we also have a P2 directly on the lateral load resisting system, the cantilever, that gives us a P2 times delta second as well at the base of the cantilever. So we've got additional side sway moment. And let's drill down into that. So the alpha P story here is P1 plus P2. You can say let's suppose those are factored loadings for some load combination we're checking. And again, alpha is 1 for LRFD. We won't bother to talk about 1.6 and needing to scale from working load level to strength and then divide by 1.6 again to get back to working load.
Can we say that in the sway problem, small delta is same as capital delta?
In the sway problems, is small delta the same as capital delta? Not quite. Yeah, and this is a good example to kind of understand some of that. So what am I doing here? I'm going to simply focus on the lateral load resisting column now, with the load P1 times delta second over L being transferred to it. So there you have it. Okay? So same system, but now just focusing on a free body diagram of the cantilever. And again, alpha P story is P2 plus P1. That's their total story vertical load. So now let's put a coordinate system on the column. A convenient coordinate system here is at the top of the cantilever, origin for X. So little delta is the deflection relative to the chord between the member ends. Okay? The deflected chord. And so if I have a column that's just falling over and that has no bending in it, there's no small delta, right? So that's what's happening with the leaning column on the right. But since the lateral load resisting column has some bending in it, I have some deflection relative to the chord between the member ends in the deflected configuration. So I have some P small delta in addition to the large delta. Right. Well, yes. So if there's no axial load, there's also no P small delta because there's no P. So the chord is between the deflected member ends, right? And then we have, because we have bending in the cantilever, the reference axis of the cantilever is offset from the chord at different positions along the length, right? If it's just a horizontal load, then yes, it's a sway problem. If there's no P, there's no P small delta, correct? Yeah, so you can have zero P small delta by having zero P, or by zero delta, right?
My question is, when I see
Right.
the small delta,
Uh-huh.
so even then they
Right, so you have a small delta, but if there's no P, then you have 0 times delta, so 0 P times delta, right? Okay?
thank you.
Okay, great. All right, so I'm going to, let's put up a moment diagram. And so this moment diagram is basically splitting the moment into 3 parts. The dark gray part is the first order moment, 8 with HL at the base. The light gray part, as you could say, is the P large delta part. If we neglect the curvature of the column and the fact that we get some additional moment due to the P times little delta here, then we would have just the gray part. So that's a P large delta effect. P1 plus P2 times delta second times X over L would be the variation in that moment. And then we have P2 times little delta, where little delta is relative to that chord, right? So now some more algebra. You say, well, what's delta? How do we define delta? So here we're going to invoke some approximations. If we're right at buckling in this system, then the equation at the top of the screen is basically what delta you would have. That would be the form if it's buckling. If it's very small P2, it would be a cubic equation, right? So this is just to be able to work the approximation here. We need some form for a curve to approximate a delta. Then the next equation there of delta second, you may recognize that it's really just a matter of doing moment area. Everybody still do moment area in undergraduate analysis here? Okay. We don't sometimes. All right. So from there, if we just solve the integral, we get terms that look a lot like what we had before, but then the last term, P2 times delta second over L times other stuff that comes from the integration, the 3 divided by pi over 2 squared minus 1. And so that term in the square brackets, the value we get for that is 0.216. And that's often taken as, if you do this for various problems, if you have a cantilever like this, or if you have a fixed column fixed against rotation at both ends and lateral loading, you'll get a C sub L of 2.216 there also. C sub L is what's coming out of that bracketed term. And so you can see I've replaced the bracket there in the bottom equation on the right by CL2 for column 2. And 3I over L squared, that's replaced that by PL story. We replace P1 plus P2 by alpha P story. That's our total vertical load, right? So now we can simplify that equation. So now that we've defined a term C sub L, when Bill LeMessurier published his seminal paper that introduced a lot of this, it's in the AISC Engineering Journal in 1977, but I typically don't use that and don't provide that because it's all in allowable stress design, so you got a lot of ugliness to work through all the allowable stress stuff. But he would calculate he actually had charts where you could go in and calculate a C sub L for every column in the frame. Now that's a lot of work. And so it was decided, no, we've got something here that's an approximation, and generally you don't want to spend a whole lot of work working something that's already very approximate, right? And so we're going to basically say that, well, in general, let's convert the equation that we were just looking at to the form you see now in the lower left, where we're going to have an alpha P story times a 1 plus an average of the CL terms over all the columns in the story. Okay? And then times delta second over L. And so what would be the CL average here in this particular case? It would be CL2 times P2 over P1 plus P2. You could say that's a weighted average, actually. Okay? So now a lot of algebra. You can see that the equation we just had here, again, same problem we had before. We've got delta second on both sides of the equation. So we need to solve for delta second. So if we do that, and we carry everything through, you get this. Form on the right down here. We have an alpha P story times a 1 plus the CL average over the columns in the story. In the numerator here of that term inside the denominator. We're going to change variables here, and we're going to introduce a new variable that's in Appendix 8 in the AISC specification called R subscript M. That's equal to 1 over 1 plus CL average. And so if we rewrite this equation in terms of RM, we get a simpler form. So RM multiplies PL story. And now RM, well, what can we write for RM? Well, here we make a very broad approximation in the AISC standard that RM we can generally write as a function of what's the total load on moment frame columns. So in this example, the cantilever was a moment frame column because it's bending under lateral load or lateral displacement. The leaning column was not. That's a leaning column or a gravity column. And so in this case, my PMF would be P2 my P story would be P1 plus P2 in this simple example. But generally, we would basically get those two items. Total vertical load is P story, supported by the story. Total vertical load supported by moment frame columns, that's PMF. And so if you've got everything in the story is a moment frame column, PMF is equal to P story, or vice versa. You get 1 minus 0.15, R sub M is 0.85, which is a rough approximation of as the worst you get. Now, what are we doing with all that? So notice the CL term, the RM term, it's all dealing with, I have some P small delta effects, but it's a side sway problem. So RM, or previously Lemessurier's CL, is dealing with what's the influence of P small delta in my columns on the large delta. Okay? You say, oh, I'm solving a drift problem. That's a large delta. But you're getting bending in the columns. You've got some small delta effects that are influencing your drift. All right? So that's the final form that we end up with in Appendix 8 of the AISC standard. And so this term that I'm writing here as 1 over 1 minus alpha P story divided by RM divided by PL story, that's basically what AISC refers to as B2, the side sway amplifier. Question?
So P story and PL story, so can it be same, the vertical load and the first order horizontal P?
Okay, the P story and the PL
PL
story?
Yeah.
So the PL story is your story stiffness.
Story stiffness,
So
first
given
order.
a story shear
Shear.
and a delta due to that shear,
Sure.
PL is your H divided by delta H over L.
Yeah.
L is your story height.
Okay.
Okay, so that's a stiffness.
Stiffness. Yeah, actually it's not related to each other. But if in the last equation, if you just see the previous slide,
Okay,
so if the P story and PL story is going to be same, so this downside, that 1 minus alpha times this one, so it will become like minus 0.85, something in the range of that one.
for the
So
amplifier?
yeah.
Yeah,
So the second order, this delta second D, means second order deflection is quite higher than the first order itself.
right. In fact,
In the negative,
in
the
became a
negative
negative
direction.
term, right?
Yeah, with negative
Yeah.
and quite higher,
That's
like
what
1.2
happens.
times.
Yeah, that's what happens with the amplifier when your term in the numerator there, the alpha P story, if that's larger than the term in the denominator, the RMPL story, then you get a negative number, but you already have exceeded the buckling load.
Yeah,
Where we're
it's
going with
negative
this
and
next
higher
is
as well.
RMPL story is actually the side sway buckling load, and that'd be another reason why we actually call it PL story.
Okay.
Did I confuse you? Go ahead. Yeah.
No. So my question was, is it with the second order this one deformation can be 1.2 times or in that range 1.2 times of first order? This much amplification can happen like that.
Yeah. Generally, we definitely do not want alpha P story to be close to RMPL story.
PL story, yeah.
If it is, we're on the verge of side sway buckling of the frame.
Okay, okay.
Okay,
Yeah.
and again, I think that's where writing the equations in this way is so valuable, because it's really all about story stiffness. So you've got, I've got vertical load. Obviously, that's important. But then, aside from the vertical load, what's your story stiffness? You have those two, then you can get your head around, okay, what sort of amplification am I dealing with? Right?
Okay, thank you.
So these are the equations. I'm just bringing them forward from the last page. Again, the equation numbers on the right in red are equation numbers that show up in the PDF of the spec, the AISC specification that you have. Again, we can do the same thing with buckling. Okay, so when do we get buckling? Well, the amplifier becomes unbounded. So if we put a gamma critical to scale up our alpha p story in the equation. Okay, well, when gamma critical times alpha p story is equal to Rm PL story, we would have buckling. So it means Rm times PL story is our side sway buckling load of the story. Appendix 8 calls that P subscript E story. PE story for the story side sway buckling load. And if we want to know, well, what's the eigenvalue or what's the multiplier to get from our design load level alpha P story to incipient buckling, or obviously that's the ratio of the buckling load to the load that we're designing for.
So by including the small delta effects, is it actually becoming better?
RM is generally going to be a number smaller than 1.
Yeah, so that's
Or in the best case scenario, if we go back to the first example where all the load was on the leading column, R sub m would be 1 in that case because there's no load on the moment frame column. And so in that case, you end up with 1 minus, I should have just taken all the alphas out. 1 minus P story over RM PL story. Okay?
So my question is, if I include the small delta effects, will it say that my frame will buckle at a
Smaller load.
right?
Smaller load. That's correct. This P small delta, just like the P large delta, is destabilizing when we have the downward load. And so writing things in terms of the drift ratio, we could write it as, well, B2 is simply same form again, 1 over 1 minus 1 over gamma critical story. All right, let's do the moment. So similar to what we did before, we're going to say, okay, well, fundamentally, the second order moment is HL plus alpha P story times delta second. And let's plug in for delta second in terms of delta first times our amplification factor. And now a lot of algebra. Manipulate that, we get to the form on the lower right. Now, if you're extraordinarily observant, you will say, oh, that amplifier looks a lot like the first amplifier we did yesterday, where we had a 1 plus psi PU over PE1. So RM minus 1 is kind of analogous to the psi term that we first looked at with the P small delta amplifier yesterday. The other thing you can observe here is notice that the amplification on the side sway displacement, so that's the delta second over L equal delta H over L times the B2 amplifier. Okay, that's a simple amplification form. We like that form a lot. The true amplification of the moments will be the form that's highlighted in yellow in the lower right. Now, okay, if we look at what's going on with that, again, notice RM is generally less than 1, and so RM minus 1, it's like the psi factor yesterday, will be a negative number multiplied by 1 over gamma story. Oh, the amplification on the moment is typically going to be smaller than the amplification on the side sway displacements. Okay. All right. Well, that would be I'll say the fanciest way to write all this. But the AISC specification, LeMessurier knew this, but then as a practical design engineer, you say, okay, yeah, but I'm just going to use B2 also for the moment. I know that's conservative. So I have the same amplifier applied either to side sway displacement or to side sway moment. I'm good. Okay? But actually, that's a conservative approximation. The code in the Appendix 8 amplification factor equations, the R sub m term is bringing in a P small delta effect on the drift. We'll look at some examples of that. I'm going to show a few examples. Yeah, the
sine curve.
we did make the approximation to derive the C sub L. We needed a deflected we needed a function for the deflected shape to get a small delta. So we basically took the buckled shape form
But that's a
there.
reasonable assumption, right?
Yeah, reasonable assumption. The R sub m is a gross approximation. Yeah, the formula for R sub m is kind of a gross curve fit.
0.85 may not be really 0.85.
Won't be 0.85. It's typically conservative.
It's conservative.
Typically.
So it could be
There's always a dangerous thing. Anytime you say that's conservative, somebody say, well, here's a case where it's not. I can show you a case where it's not conservative, but it typically is. We'll look at some very interesting things that are surprising here sometimes in what we're going to be discussing. All right, we talked about the effective length factor K1 for non-sway yesterday. And again, remember, I emphasized at the beginning of class today that you don't need the K factor. You just need the load in the member, axial force in the member at incipient buckling when you design from that. So if you're using computations, you can work straight from that. But you still may want to calculate a K factor because it helps you kind of understand what's going on, right? And that's where I always tell my students at Georgia Tech, the effective length method is a misnomer. It's the buckling analysis-based method. It's not the effective length method. With that said, let's talk about getting a side sway effective length factor. Whatever you're doing, non-sway, side sway, it really just comes down to what I'm showing you at the top of the screen here. You take your axial load in the member at buckling, so 1,001 different ways, different tools, different charts, different equations that you can use to estimate that load. Gamma critical story times alpha PR, that's your load in the column at buckling. All right, let's equate that to pi squared EI, I left off the star here, divided by K2L squared. Okay? I think I left off the star here because when we talk about effective length, that's usually the effective length method. Solve for K2. Any tool that you use, that's what you're doing. It's just that it may work differently than that. So the equations I've introduced to you, I think, are what I feel are the most useful for a design engineer. In design, I want to be thinking story stiffness and how much load do I have. Now I can use different models to come up with my story stiffness. So given my story stiffness, now I'm coming down to an individual column. What's the column effective length factor? We can see it ends up into a fair amount of complicated things here that can simplify down to P story over PR. PR stands for the required loading. It's what you're getting from your analysis. It's the loading you're designing your column for. It's equal to PU if we were just doing LRFD. Should just change all these to sides to LRFD and we could take out the alpha and we can just use a PU. We got a pi squared E over L squared. Oh, that's just the Euler load for that column length. We've got an RMPL story. Oh, that's the story elastic buckling, side sway buckling load. So if you got those, you can calculate the individual column K2. And if we write it into the form that you see here, that's one of several equations for effective length factors in sway frames that shows up in the AISC specification commentary. In my view, this is absolutely the most useful of all of them. It's not, all of the other ones are fine. It's just like how many different ways do you need to calculate a K factor? I think you only need one, and it's this one. Now, the measure is the one that gets the credit for essentially putting this together. When he did his work, what we're going to look at some cases. Tomorrow we'll look at a case where it's a sway frame, but for a column that's a very light column in the sway frame, you actually get the other portions of the frame that very light member on its own doesn't have much stability. So the rest of the sway frame is essentially bracing that member. And so it's a sway frame, but you're actually getting an effective length factor less than 1 for that very light member. That's confusing to a lot of folks because we're used to using tools where we say, oh, it's a side sway, K is always greater than 1. No, it's not. When you come to graduate school, then you find that, oh, sometimes it's not. And we'll look at a good example of that tomorrow.
So the K2 calculated here applies to all the columns in that.
Any individual column, you can get a K2 value for it. K2 is an individual column parameter.
But the formula, where does the column information come in?
Where does what come in?
So let's say I have 4 columns in FA.
Mm-hmm.
Right? For each column, if I have to calculate K2,
Mm-hmm.
how would that formula be different?
Okay, so the EI would be different for each column. And the PR would be different, or PR equals PU for LRFT would be different for each column.
Is the same for all the columns. Then
Okay.
K2 is the same for all the columns.
If EI is different for the different columns, then K changes.
So basically based on the EI of the column and the PR.
In other words, if you have one column that's got a really big EI, it's going to take more of the work to stabilize the story than this little guy over here, right? So the guy with the big EI is going to end up getting a big K factor. The little guy is going to say, "Oh, I'm getting a lot of help. I'm leaning on this guy over there. Oh, I'm actually have a K less than 1." Okay. Now, this derivation has its limitations in that, and we'll look at that. We'll explore those a little bit with one of the frames tomorrow. You can have a situation where you start having a light column that's getting a small effective length factor. It may be erroneous because of the approximations with dealing with small delta in this derivation. And so what Lemessurier did is he did a whole bunch of parametric studies and then came up with an inequality to restrict how low your K2 value for a really lightweight column can be. Now, many engineers will simply say, oh, it's a sway frame, just design everything at no less than K equals 1. And I think I find that to be an acceptable approximation. Lemessurier would have, if he were still alive, may have argued it differently. He felt that his equation in some cases would not let you go that low. So that inequality is sometimes a bit confusing because anytime you've got something that's empirical and it kind of comes out of the blue, where did this come from? Well, it's a big curve fit to a whole bunch of parametric studies. If you have something like the leaning column we started with over on the right, pin at the top, pin at the base in terms of your idealization, K is equal to 1. You could apply this equation to such a column and get a K factor other than 1, but no, it's pin. It's K equals 1. Okay? Then comes the thing that's really confusing with buckling-based solutions with side sway. You say, but I've got a very light, very flexible spring connection. That connection represented by a spring to top and bottom to a column over there on the right. Okay, now you get into something where that in the literature is referred to the effective length factor paradox, where it's really more not so appropriate to use this really large K factor for something like that because it's not really helping the story. You're just penalizing the column. So that's a very hand-waving. If you want to learn more about effective length factor paradox, you could Google that and pull up some of the literature on it. It's the effective designing with effective lengths or with buckling solutions isn't perfect. We'll look at some places where that kind of becomes a little bit difficult.
So why would we want to?
Let's say you've got a structure and you don't want a bracing diagonal going through your doorway, or you need access. Yeah, moment frame would be a sway frame. That's correct. It's obvious it's always going to be more efficient if you can have walls or bracing systems in the frame. But in some situations, we want to use a moment frame. That's correct.